Hi guys, welcome to today's lesson looking at integration of exponential functions, so the opposite of differentiation. So if you haven't looked at the lesson on differentiating e, then certainly go ahead and do that first of all. Okay, so basically we're looking at integrating exponential functions. So in order to do that, what we're going to do is look at differentiation just first of all, which we did the last lesson. So we had e to the power of 2x. So if we wanted to differentiate this particular function, we would take the derivative of the power, so which would be 2, and then we have the same function e to the 2x. So what we want to do is to go from dy dx and back to e to the power of 2x. So how do we do that? Well, we're going to do the opposite. So here we times by, or basically times by, the derivative of the power. So what's the opposite of times by? Well, it's divide by. And the good thing is, you'll notice that when we're looking at this term, that has not changed from the original function. So the great thing is, if we get a question which is dy dx is equal to 2e to the 2x, and we're asked to find, in this case, the primitive function, which would be y is equal to, what we can look at is just do the opposite of times by the derivative and just divide by the derivative of 2. So 2 divided by 2 is just 1, so we get e to the power of 2x, and that's what we started with. Can you see what's the one thing I've forgotten to do? I've forgotten to put that plus c, okay, because that could have been e to the power of 2x plus 4. We don't know, okay, so we have to still put that plus c. Some people put plus k, okay, it's just plus a constant. So let's have a look at some questions here. Find the integration or the integral of e to the power of 2x minus e to the negative x. Okay, now this is what we would call an indefinite integral, okay, because there are no bounds here, there are no limits here for our x values, so we're just finding we're just integrating that particular function. So we've got e to the power of 2x, so that's similar to one we just did previously. So what's the differentiation of 2x? Well, that's just 2, but instead of timesing by 2, that's what we would do if we were differentiating. We are dividing it by 2. Likewise, for the next one, we've got e to the power of negative x. Okay, if I find the derivative of negative x, that's negative 1, I'm going to divide by that amount. Okay, and then I'm going to put a plus c on the end of it. So let's just fix this up. E to the power of 2x over 2. Now, negative makes positive. Over 1, that can just leave off, negative x plus c. And that is my final answer. You could even write it, if you wish, you might want to write as a half e to the 2x plus 1 over e to the x plus c. That's just a different way you could write that particular function. A half e to the 2x is the same as e to the 2x over 2. They're the same thing, and obviously you should know that e to the negative x will be the same as 1 over e to the power of x. Alrighty. Question 2. Find the area between the curve. Well, remember, area between the curve means the integral of y is equal to e to the power of 3x. So e to the power of 3x dx with the x-axis and the lines x equals 0 and x equals 2. So in this case, we have those bounds there, 0 and 2. I guess if you sketched it, and often go back from my previous lessons on integration, I like sketching. I think it's a really good thing to do. E to the power of 3x looks something like that, which is an exponential curve. And we're going to have some limits on there. Okay, so we're going to have 0, which would be here, and 2, so that's 1, 2. So basically what it's asking me to do is to find the area of that section there. So basically we're simply trying to find the integral of this amount here. Okay, but we're going to be putting it in our square brackets because remember we call this a definite integral because I'm going to come up with a definite value. There are bounds there. Okay, so we've got e to the power of 3x. So e to the power of 3x over, and then I'm going to come up with, well, if I differentiate 3x, we get 3, so I'm going to divide by 3. And I'm going to put that there as 2 and 0. Now remember, we don't have to put the plus c there because the plus c, when I do my subtraction, the c's will cancel out. Okay, so now we can actually substitute. So we're going to have e to the power of 3 times 2 is 6 over 3 minus e to the power of 3 times 0 is 0 over 3. Now, if you recognize that that's going to be, well, it's not going to be 0, is it? That's interesting. So that's good. So we've got e to the power of 6 over 3 minus, well, e to the power of 0. Anything to the power of 0 is just 1. So we get that amount there. So we could leave it that way if we wished. Okay, you could even factorize 1/3 out and then put e to the power of 6 minus 1. Okay, you could do that as well. All right, that works out nicely. Okay, so again, all I did there is I integrated e to the power of 3x by differentiating the 3x, which is 3, and then dividing it by 3. Then using our integration rules when we are finding the area underneath the curve between 2 points, so we've got limits there, or our interval, we put our values of x, 0 and 2 there. We then subtract with substituting the values of 2 into where x is and 0 where x is, and then work from there. Okay, and because it's area, I chuck on units squared at the end of that. You could go ahead, I guess, I mean, that would be the exact value. You could go ahead if you wished. If it's said to a certain amount of decimal places, all I do is get my calculator out. I'll type that in left to right, making sure that you're using the value of e on your calculator, which is often Shift LN, and then simply typing it in. If I did that, and it said, let's say to 2 decimal places, it'd be 134.14 units squared. So I could either give that as an exact value, or I could do it as a decimal place. If it was asked a decimal place, you wouldn't have to bother doing the factorizing, but certainly a lot of questions do ask for the exact value, so that's important for us to do that. Okay. And the last question, I thought I'd throw in a volume question. Okay, so we're tying everything together now. And it's the same with what we've done previously with volume, but it's just looking at using the e as part of our integration. So it says find the volume of the solid revolution formed when the curve y is equal to e to the power of x is rotated about the x-axis from x equals 0 to x equals 2. Alright, so we need to remember the rule for volume. So volume equals the pi times the integral of y squared times y squared dx. So in this case, we've got y is equal to x. So what we want is what y squared is equal to. Well, that means we're going to square e to the power of x. What happens when one's inside, one's outside the brackets? We multiply. So y squared is going to equal to e to the power of 2x, okay, because 2 times x is 2x. So that means when I'm doing my volume, I'm going to have pi times the integral of e to the power of 2x dx. Now it's between the values of 0 and 2, same as that last question. So equals, or approximately equal to, pi times the integral. So let's integrate e to the power of 2x. Well, that'll be e to the power of 2x divided by, well, if I differentiate 2x, we get 2. So you divide by 2. And then we get between 2 and 0. So pi times, alright. So now we're going to substitute. E to the power of 2 times 2 is 4 over 2. minus, and then e to the power of 0 divided by 2. And remember, I should put, I might put that in green, a set of brackets there, because we're timesing that whole integral by pi. Now, again, what you can do, if you are asked for the exact value, the exact area, we could take out the half, okay, because what that's going to be is just, I guess, pi times e to the power of 4 over 2 minus e to the power of 0 is 1 over 2. You could just take out the half and do a half pi, or pi divided by 2, and then have brackets e to the power of 4 minus 1 units cubed. Remember, we're doing volume. So we could just leave our answer as an exact value if we wish, but also if it asked us to find, let's say, to 2 decimal places, we could then simply type that into our calculator as it reads left to right. And you could do it without the factorizing if that's the case. But either way, if you did that, you would get 84 point, we'll do 2 decimal places, 19 units cubed as your answer for the estimation around the curve of the volume. Remember, that volume is looking at something like this. It's an exponential curve between 0 and 1, so 0 and 2 there. Remember, we're going about the x-axis there, so it's kind of looking like the cone sort of around there. But yeah, you can sort of get what I mean. But if you round that around the x-axis, it kind of looks like this. Kind of looks like that, bit of a curve or a cone, I guess. But you don't have to really have a diagram for that, but you can if you wish. So look, it's a much harder question, I guess, because it's volume. Often that's a question where people do have a few issues with. But remember, volume actually isn't that much harder. It's just doing the same what we did for the last question for the area, but you're timesing it by pi, and it's no longer just y dx or f of x dx, it's y squared. So you need to make sure that you do convert that to the beginning part. But again, that's your volume. If you can't remember how to do volume, then you need to go back and watch that lesson on integration with volumes. Anyway, I hope that made a bit of sense, guys. Remember, it's just the opposite of our differentiation rules for exponential functions. So I guess, if we came up with a generalization rule, as we did before, if you've got f of x and you want to integrate f of x dx, then all you're doing is doing actually we should put, sorry, let's scrap that, e to the power of f of x dx. Then all I'm doing is my e to the power of f of x divided by f dash x. So we're just integrating it and then dividing it by that integration, sorry, that differentiation. Anyway, I hope that made sense, guys. Let me know if it didn't. I can redo it, but it should be pretty straightforward. Have a great day.